Okay, so energy budgets. The amount of available energy that is available, okay, is going to determine how much photosynthesis occurs. Okay, so the amount of light energy that gets converted to chemical energy during a given time, amount of energy, a certain area, a certain time represents the storage chemical energy that will be available to consumers, our primary productivity. Well, when we subtract respiration, and remember, a lot of people forget this, that plants will also respire. Okay, they'll burn up some of that primary productivity, the gross primary productivity. So when we subtract that, that's the actual available energy in the plant, the net primary production. So production efficiency, here we have a herbivore, and this herbivore is eating 200 joules of plant material, okay? 67 joules is lost to heat. 33 joules is used, and 100 joules is lost to feces. Now remember, that feces are going to be eaten by detritivores, and most of that energy isn't going to get lost as heat. So how much was converted? 33 joules out of the 200 joules was converted, and we call that secondary production. And out of all the energy that was used, we don't include the feces, 33 out of 100, 33% was the production efficiency, the percentage of energy stored in food that is not used for respiration. So energy flows, it does not cycle, and throughout all of this, energy is lost as heat, and heat here. Only a small percentage is kept. So trophic efficiency speaks to how much energy is passed on to the next trophic level. So the percentage production transfer from one to the next, and this sort of explains why there's not more than 5 trophic levels in a food web food chain, simply because no more energy would be left. And we essentially call this a 10% rule. Of the original energy from the sun, only 10% is passed on, 90% is lost. 10% of 10,000 is 1,000, and that 9,000 joules would be lost. 10% of 1,000 is 100, 900 joules is lost to heat, and so on and so forth as we go up the trophic levels. So energy is lost at each step in the food chain. Of the general estimate is 90% is lost, so 10% is passed on, the 10% rule. So this gets to us to these pyramids. There's a loss of energy with each trophic level. So at higher trophic levels, there's less biomass, less numbers, and larger body sizes also. The body sizes tend to increase. There's 3 types of pyramids. Pyramid of numbers is just as it says, okay? Pyramids are based on data from a given area. So some poor person would have to count in a certain area, a kilometer squared, how many pieces of grass and so on in that area. And then they would have to, in that same area, count how many mice, how many snakes, how many birds of prey. And they would get a pyramid that looked like that. However, sometimes you get an inverted pyramid. What would happen if we had in one area one oak tree? And then we counted all the herbivores on it. Well, there'd be way more herbivores in the one oak tree. So we get this inverted pyramid. And you will get this in marine systems as well that I want you to read about. So usually when there is a large number of herbivores per producer or a very large producer. And the large number of herbivores per producer is in marine ecosystems. And again, you'll do a reading assignment on that. Pyramid of biomass is just the dry weight. Okay, so if we take all the weight out of this lemming, okay, and weigh it, all the water out of it and weigh it. So now look at the units, grams per meter squared. And again, we get a pyramid. Pyramid of energy, though, is the most specific one. It counts the joules. And we will always get a pyramid that looks like this, where we're measuring energy. So here we have a deciduous forest versus a grassland. Okay, and a comparison of the two. So this raises a few ethical questions. Can we feed a larger population if humans we ate only plants? Well, if we only ate only plants, we'd only have one energy transfer. Okay, here we're going to have two energy transfers, and with the 10% rule, we're going to have much more energy lost. So this is why they say if you're really concerned about ecology and the state of the planet and habitat loss, we should be clearing less land for cattle and eating the corn directly because we'd have to clear a far less land. This would take acres and acres and acres to grow up all those cows. Here, we'd only need a few acres to grow up all that corn to feed the same number of people. Less energy loss. Okay, and there's another analysis of it. Same with the oceans as well. So I'm going to talk about this in the last brief slideshow.